What's everything made of? Look around you. The chair you're sitting on, the air you're breathing, even the stars twinkling in the night sky. What's the smallest piece holding it all together? It's a question so simple yet so big, it's been bugging humans for thousands of years. From ancient philosophers scratching their heads under olive trees to today's scientists peering through microscopes, we've all wanted to know, what's the real stuff of the universe? The universe is like an onion. Peel back one layer and there's another, each more mind-blowing than the last. Long ago people thought everything came down to four basics: earth, water, air and fire. Nice try, but not quite. Then we cracked open the atom, tiny invisible building blocks buzzing with energy. But wait, there's more. Inside atoms we found even tinier bits, electrons, protons, neutrons, and then a whole wild crew of particles dancing to rules we're still figuring out. Now, we're on the brink of something huge. Quantum fields that hum with mystery, a lineup of particles so strange they sound like science fiction. This isn't just a story about tiny things, it's about us, about what makes you, me, and the whole cosmos tick. In today's documentary, we zoom into the smallest corners of reality and uncover what we're really made of. Let's dive in. Imagine a time when the world felt like a grand, unsolved mystery. Thousands of years ago, humans stared at the sky, dug into the earth, and wondered, what are we made of? It's a question that burned in the minds of ancient philosophers, flickered in the dreams of alchemists, and finally found a spark of an answer in the 19th century. That spark came from a man named Dmitri Mendeleev, a Russian chemist with a wild beard, and an even wilder idea. In 1869, Mendeleev sat down with a stack of cards, each scribbled with the name of an element, those basic ingredients of reality, like oxygen, iron and gold. He started arranging them, not by whim, but by a number, their atomic weight. As he slid the cards into rows and columns, something extraordinary happened. The elements began to align, like pieces of a cosmic jigsaw puzzle. Elements that burned or shimmered in similar ways fell into neat groups. It was order out of chaos. A table that didn't just list the building blocks of the world, it predicted them. Mendeleev didn't stop there. He left blank spaces on his table, bold gaps where he swore undiscovered elements belonged. He even guessed what they'd be like, how heavy, how reactive. And when those elements, like gallium and germanium, turned up years later, they slipped into place with a precision that stunned the world. It was as if he'd glimpsed the future through the lens of the present. Mendeleev's periodic table, for all its genius, was a teaser, not the full story. It showed us the what, the elements, but left the why dangling like a cliffhanger. Why did helium float while lead sank? Why could carbon bond with almost anything, while neon stood aloof? The table was a beautiful map, but it didn't tell us what lay beneath the surface. And as the years rolled on, it grew, stretching to include bizarre lab-made elements like organesson, fleeting visitors that blinked into existence for milliseconds. By 2016, the table's seventh row was complete, but a whisper persisted. Is this all there is? The periodic table wasn't the end. It was a starting line, a tantalizing hint that the real secrets of matter lay deeper, beyond the elements, waiting to be unearthed. The elements were just the opening act. By the late 19th century, scientists were restless, itching to peel back the layers of the atom, once thought to be the smallest indivisible speck of matter. The first crack in that idea came in 1897, from a man named J.J. Thomson. Picture him hunched over a glowing glass tube, watching cathode rays dance inside. Were they light? Were they something else? Thomson fired up his experiments and found the answer. Tiny, negatively charged particles, far smaller than any atom. He named them electrons, and with that, the atom split open like a cracked walnut, revealing a hidden world within. But the plot thickened. In 1911, Ernest Rutherford, a former student of Thomson's, took the stage. He hurled alpha particles at a whisper-thin sheet of gold, expecting them to sail through. Most did, but some ricocheted back as if they'd slammed into a brick wall. Rutherford's jaw must have dropped. He realized the atom wasn't a solid lump. It was a vast emptiness, with a tiny, dense nucleus at its heart, orbited by electrons like distant stars. It was a cosmic dance, a miniature universe inside every speck of dust. Yet this dance had mysteries of its own. Why didn't the electrons crash into the nucleus? Why did atoms glow with specific colors when heated? The old rules didn't apply, and a new science, quantum mechanics, stepped in to rewrite them. In the 1920s, minds like Niels Bohr and Werner Heisenberg painted a wilder picture. Electrons weren't orbiting neatly. They buzzed in smeared, ghostly clouds, their whereabouts a roll of the dice. Reality, it seemed, was less certain than we'd ever imagined. Then, in 1932, James Chadwick dropped another bombshell, the neutron. Tucked inside the nucleus alongside protons, this neutral particle completed a trio: protons, neutrons, electrons, three pieces to build everything we know. It felt like the end of the road, a tidy answer to an ancient question. But nature loves a twist, and this was just the setup for a stranger tale, one that would take us deeper still. By the 1950s, physicists were smug. Protons, neutrons, electrons. It was a clean, simple recipe for the universe. Then they built machines, particle accelerators, that smashed atoms together at breakneck speeds, and the kitchen got messy. Out of the wreckage spilled a flood of new particles, pions, kaons, muons, a chaotic parade of oddities that defied explanation. They called it the particle zoo, and it was a glorious, bewildering disaster. How could so many fundamental pieces exist? In 1964, two daring thinkers, Murray Gell-Mann and George Zweig, stepped into the chaos with a hunch. What if protons and neutrons weren't the bottom line? What if they were made of something smaller? They dreamed up quarks, elusive bits that combined like Lego bricks. A proton, two up quarks and one down. A neutron, one up, two downs. It was elegant, but there was a hitch. Quarks were phantoms, locked tight inside their hosts, never seen alone. Skeptics scoffed, but the evidence crept in. By the late 1960s, experiments at Stanford pinged electrons off protons, revealing three tiny blips inside, like shadows of quarks caught in the act. The particle zoo wasn't a mess after all. It was a kaleidoscope of quark combinations. Suddenly the universe slimmed down to a trio again. Electrons, up quarks, down quark. These three, plus a few others, built atoms, molecules, us, everything. In 2012, the Large Hadron Collider sealed the deal with the Higgs boson, the particle that weaves mass into the fabric of existence. The standard model of particle physics stood tall, a map of all we knew. But as the champagne flowed, a shadow loomed. Is this the final chapter? Are quarks and electrons the smallest dots in the cosmic painting? Or are they brushstrokes hiding an even deeper canvas? The quest isn't over, not by a long shot. What we're made of might just be the strangest story yet to unfold. Imagine a world where electricity is a parlor trick, where magnets are curiosities pulled from the earth, and the invisible forces that move them are as mysterious as the tides to a medieval sailor. It's the dawn of the 19th century, a time when science is still shaking off the dust of alchemy, and into this world steps a man who will change everything. His name is Michael Faraday, and he's no aristocrat with a university degree. He's the son of a blacksmith, born in 1791 in a cramped London suburb, a boy who taught himself to read from the books he bound as an apprentice. Yet within this unassuming figure burns a curiosity so fierce it will light up the modern age. Faraday doesn't just want to know what happens, he wants to know why. In the 1820s, he's a young man working at the Royal Institution, surrounded by glass jars, copper wires, and the hum of possibility. Scientists before him had played with electricity and magnetism, but they saw them as separate, disjointed forces, sparks in the dark, tugging at iron filings. Faraday sees something more. He's obsessed with the idea that these forces aren't just random, they're connected, woven into the very air around us. It starts with a simple experiment. Faraday takes a coil of wire, a magnet, and a hunch. He moves the magnet near the coil, and something miraculous happens. A current flows, not a spark, not a jolt, but a steady stream of electricity, born from motion alone. This is 1831, and he's just discovered electromagnetic induction. It's a quiet moment in a cluttered lab, but it's the spark that will ignite the Industrial Revolution. Generators will hum, cities will glow, all because Faraday saw what others missed, that a changing magnetic field can reach out and stir electricity into being. But he doesn't stop there. Most scientists of his day think forces act like invisible hands, grabbing objects across empty space. Faraday disagrees. He imagines something wilder, something alive. He pictures the space around a magnet or a charged object not as empty, but as filled with what he calls lines of force, tendrils of influence stretching out, curling, weaving through the void. To him, a magnet isn't just a lump of iron, it's a source of power, radiating a field that ripples through the air, ready to nudge anything that dares to cross its path. This isn't easy to prove. Faraday isn't a mathematician spinning equations on a chalkboard. He's a hands-on visionary, sketching his ideas in notebooks, building contraptions to test them. He dips wires into jars of salt water and watches as electricity splits molecules apart. Electrolysis, he calls it, revealing that electric fields can tug at the very building blocks of matter. He wraps coils around iron rings, showing how magnetic fields can leap from one side to the other, linking the two forces in a dance of energy. The scientific elite scoff at first. Fields, they say, show us the proof. But Faraday keeps going, piling up evidence until even the skeptics can't ignore him. He's not just tinkering, he's rewriting the rules. By the 1860s, a brilliant Scotsman named James Clerk Maxwell takes Faraday's vision and turns it into mathematics. Equations that show electric and magnetic fields aren't separate at all, but two sides of the same coin, rippling through space as electromagnetic waves. Light itself, Maxwell realizes, is one of these waves, born from the fields Faraday imagined. Faraday's no poet, but his words carry a quiet power. The beauty of electricity, he writes, is not that the power is in the wire, but that it is everywhere around it. He's telling us that the world isn't just stuff, metal, wood, flesh. It's the spaces between, alive with forces we can't see but can feel. His fields are the first glimpse of a universe that's more than meets the eye, a tapestry of energy that ties everything together. Faraday's discoveries don't just sit in history books. They're in the hum of your refrigerator, the glow of your screen, the buzz of every power line stretching across the horizon. He took the invisible and made it real, showing us that reality isn't solid. It's a web of fields, humming with potential, waiting to be tapped. But as profound as his vision was, it's only the first thread in a much stranger story. Faraday's fields opened a door, but what lay beyond was a realm so alien, it would have boggled even his brilliant mind. Fast forward to the early 20th century, when science is digging deeper, peering into the guts of atoms, and finding a universe that doesn't play by the rules we know. This is the birth of quantum mechanics, a revolution that turns everything we thought we understood upside down. And it starts with a question that sounds simple but isn't. What is light? For centuries we'd argued about it. Isaac Newton said light was a stream of particles, tiny bullets shooting through space. Others, like Christian Huygens, insisted it was a wave, rolling across the ether like ripples on a pond. By the 1800s, experiments with diffraction, light bending around edges, seemed to settle it. Light was a wave, carried by Faraday's electromagnetic fields. Case closed, until a German physicist named Max Planck threw a wrench into the works. In 1900, Planck is studying how hot objects glow, and the math doesn't add up. Classical physics says they should radiate infinite energy, which is nonsense. They don't. So Planck suggests something radical. Energy doesn't flow smoothly. It comes in chunks, little packets he calls quanta. 5 years later, Albert Einstein takes it further, saying light itself is quantized. Those waves are also particles, photons, each carrying a precise punch of energy. Suddenly, light isn't just a wave. It's a particle too, and it's both. And that's when things get weird. If light can be two things at once, what about matter? In 1924, a French nobleman turned physicist, Louis de Broglie, has a crazy idea. If light waves can act like particles, maybe particles can act like waves. He's laughed at electrons, those tiny bits orbiting atoms, as waves. But then, in 1927, Clinton Davison and Lester Germer fire electrons at a crystal in New Jersey, and the results stun the world. The electrons scatter into patterns, bands of light and dark, just like waves interfering with each other. De Broglie was right. The double-slit experiment seals the deal. Picture this. A gun shoots electrons at a barrier with two narrow slits. Behind it, a screen catches whatever comes through. If electrons are particles, you'd expect two stripes on the screen, one for each slit. But that's not what happens. The screen lights up with a zebra pattern, stripes of bright and dim, a telltale sign of waves crashing into each other, amplifying here, cancelling there. It's as if each electron doesn't pick a slit, but goes through both, spreading out like a wave, only to snap back into a particle when it hits the screen. Now, if you put detectors at the slits to catch the electrons in the act, the pattern changes, the stripes vanish, and you get two bands, like particles picking a side. Look at them. and they're particles. Don't look, and they're waves. It's not just a trick of the equipment, it's reality itself shifting, depending on how we watch it. This is the wave-particle duality, and it's the cornerstone of quantum mechanics, a world where certainty dissolves into a fog of maybe. Poor. But how do you make sense of this? Enter the wave function, a mathematical ghost that describes where an electron might be. It's not a solid dot on a map. It's a smear, a probability cloud rippling through space. Fire an electron, and its wave function fans out, passing through both slits, interfering with itself. Measure it, and the cloud collapses, poof, into a single spot. It's like the universe is playing hide and seek, revealing only what it must, when we force it to. And here's where Faraday's fields come back into play. By the 1940s, physicists like Paul Dirac and Richard Feynman start weaving these ideas into quantum field theory. That wave function? It's not floating in a vacuum. It's a ripple in a field, an electron field that spans the cosmos. The duality isn't a paradox. It's a clue. Electrons aren't waves or particles. They're disturbances, vibrations in an invisible sea that's everywhere, all at once. This isn't just lab talk. In 2012, scientists in Vienna take molecules, big ones with dozens of atoms, and shoot them through slits. Same result. Interference patterns. Even these clunky clusters act like waves, as if the quantum weirdness doesn't stop at the tiny, but climbs into the world we can touch. And in 2021, researchers in Germany cool 1 billion atoms into a single quantum state, a puddle of matter waving in unison, visible to the naked eye. The line between the strange and the familiar is thinner than we thought. Quantum mechanics tells us the universe isn't a machine with gears and levers. It's a symphony of fields, each note a possibility, each chord a particle flickering into being. It's a reality where the act of looking shapes what's seen, where emptiness is a lie, and the stage is set for an even wilder act. So if electrons are waves in a field, what's the field itself? Let's zoom in on the electron field, a concept so strange and beautiful, it rewrites everything we know about matter. Imagine a vast ocean, stretching from horizon to horizon, its surface glassy and still. That's the electron field in its quiet state. No ripples, no electrons, just pure potential. Now, flick a finger across that surface, send a shiver through it, and a wave rises. That wave, that disturbance, is what we call an electron. It's not a thing sitting there, waiting to be found. It's an event, a moment when the field wakes up and says, "Here I am." This isn't a metaphor. It's physics. Quantum field theory, born in the mid-20th century, says every particle has its own field. So photons, they're sparks in the electromagnetic field. Quarks, tremors in quark fields. The Higgs boson, a hiccup in the Higgs field discovered in 2012, when the Large Hadron Collider shook it hard enough to make it sing. These fields aren't separate. They overlap, intertwined, filling every inch of space with a chorus of vibrations that birth the particles we know. But let's stick with the electron field for a moment. It's not some static grid. It's alive, buzzing even when we don't see it. In a vacuum where you'd think nothing happens, the field isn't dead, it's simmering. Quantum mechanics says fields can't sit still. They jitter, flicker, spitting out virtual particles that blink into existence and vanish before you can blink back. These aren't electrons you can grab. They're phantoms, shadows of the field's restless energy. This isn't sci-fi. It's measurable. Take the Casimir effect. 2 metal plates, uncharged, floating in a vacuum, a hair's breadth apart. They shouldn't move, right? Wrong. They drift together, pulled by a force no one can see. Why? Because the vacuum between them isn't empty. It's a storm of virtual particles, and the plates choke that storm, creating a pressure drop that tugs them inward. It's 1948 when Hendrik Casimir predicts this, and decades later we measure it. Proof that even nothing is something. Now, step back. All these fields, electron, photon, quark and more, fit into a grand blueprint called the Standard Model. Picture it. 12 matter fields, like the electron and its quark cousins, each a different flavor of reality. Add 4 force fields, electromagnetic, strong, weak, and the elusive gravitational, and you've got the recipe for everything we've ever seen. The electromagnetic field carries light and binds atoms. The strong field glues quarks into protons. The weak field flips particles in radioactive decay. And the Higgs field? It's the cosmic sculptor, giving mass to the others and making them heavy enough to clump into you and me. The Standard Model is a triumph. In 1964, Peter Higgs and others dream up the Higgs field to explain why particles aren't massless ghosts. Nearly 50 years later, on July 4th, 2012, CERN's detectors light up with the Higgs boson's faint echo, a particle so rare it takes trillions of collisions to catch us. It's the final piece, the capstone of a theory that predicts how fields dance, to build the world. But don't get too comfortable. The Standard Model is a masterpiece with cracks. It doesn't explain gravity. Not fully. Not like the others. It's silent on dark matter. That invisible stuff 5 times more common than the atoms in your body, holding galaxies together. And dark energy. That mysterious push stretching the universe apart. The model shrugs. It's like a map that gets you across the continent, but fades at the edges, leaving whole continents uncharted. So, we dig deeper. In labs and observatories, physicists chase the next frontier. At Fermilab, they fire neutrinos, ghostly particles, through the Earth, watching them morph, hinting at fields beyond the Standard Model. In Geneva, the LHC smashes protons, hunting for cracks in the theory, for new particles that might whisper of extra fields. In quantum labs, they entangle particles across miles, suggesting fields might connect in ways we can't yet grasp. Spooky action at a distance, as Einstein called it, now a tool for quantum computers that could outthink anything we've built. And then there's the big question, the one that lingers like a shadow. What are these fields made of? Are they the bedrock of reality, or are they ripples on something deeper? String theory whispers of tiny vibrating strings beneath it all, but we're nowhere near proving it. Some say fields emerge from space-time itself, twisted by gravity in ways Einstein only dreamed. Others wonder if we're asking the wrong question, that fields aren't made of anything, they just are, the raw stuff of existence. Here's what we do know. You're not just atoms, you're fields. Electron fields sparking your nerves, quark fields building your bones, Higgs fields weighing you down. Empty space isn't empty. It's a cauldron of possibility, simmering with the seeds of everything. Faraday saw the first glimmer. Quantum mechanics lit the path. And now, as we stand on the edge of the unknown, we realize the universe isn't a collection of things, it's a story of fields, weaving the past, present and future into one endless shimmering tale. Picture a time when the universe was a locked vault, its secrets sealed behind the unyielding walls of the atom. It's the late 19th century, and scientists are wielding their first keys, crude tools of electricity and vacuum tubes, trying to pry it open. In 1897, J.J. Thomson stumbles upon a spark of brilliance, the electron, a tiny speck buzzing around the atom's edge. It's the first crack in the vault, proof that atoms aren't indivisible after all. But as the 20th century dawns, the vault bursts wide open, spilling out a flood of particles. Protons, neutrons, pions, kaons. A chaotic zoo that leaves physicists scrambling. They're like explorers in an uncharted jungle, hacking through vines of data, desperate for a map. That map arrives decades later, a masterpiece of human intellect called the Standard Model. At its heart lie the matter fields, the raw ingredients of reality. Forget the idea of particles as little billiard balls. In the strange world of quantum mechanics, they're more like waves, ripples in invisible oceans of energy that stretch across space and time. These ripples are the fermions, the building blocks of everything you can touch and see or dream, and they come in two tribes, quarks and leptons, each with its own personality, each vibrating to its own tune. Let's start with the quarks, the unsung heroes of the atomic nucleus. There are 6 of them, up, down, charm, strange, top and bottom, like a quirky family with 6 siblings, each more eccentric than the last. The up quark carries a charge of +2/3. The down quark, 1/3, numbers so odd they stunned physicists. When Murray Gell-Mann first sketched them out in 1964, these fractional charges are the Lego bricks of protons and neutrons. Take 2 up quarks and 1 down, and you've got a proton, its charge adding up to +1. Swap that recipe, 1 up, 2 downs, and you've got a neutron, neutral as its name implies. But quarks aren't content to sit still. They jitter and jostle, bound together by a force so fierce. It's like cosmic cement, locking them into trios that form the nuclei of every atom in your body. What makes quarks truly wild is their organization into 3 generations. The first generation, up and down, just is the workhorse, crafting the matter of daily life. The second, charm and strange, shows up in fleeting glimpses, born in the fiery hearts of stars, or the collisions of cosmic rays. The third, top and bottom, is the heavyweight champion, with the top quark tipping the scales. At 173 times the proton's mass, so hefty it decays in a blink. Why 3 generations? No one knows. It's as if nature wrote a recipe with 3 drafts, each bolder than the last, but only bothered to cook with the first most days. Now, meet the leptons, the free spirits of the particle world. Like quarks, there are 6, split into 3 generations, but they dance to a different beat. The electron is the star of the show, a lightweight at 1/1836th the proton's mass, zipping around atoms, sparking the chemistry that builds molecules, fuels fires, and powers your brain. Its siblings, the muon and tau, are heavier, moodier cousins, 203,500 times the electron's mass, respectively. They're unstable, collapsing into lighter particles. Within millionths or billionths of a second, a cosmic fireworks display too brief to savor. Then there are the neutrinos, the phantoms of physics, and 3 of them: electron neutrino, muon neutrino, tau neutrino, 1 for each generation. They're nearly massless, chargeless, and so aloof they can pass through a light year of lead without a whisper. Yet they're everywhere. The sun floods Earth with 65 billion neutrinos per square centimetre every second, and they're sailing through you now, indifferent to your existence. In the 1990s, scientists discovered they're not just shy, they're shapeshifters, oscillating between types as they travel. A trick that earned Takaaki Kajita and Arthur MacDonald the 2015 Nobel Prize. It's a clue that the Standard Model might be hiding something bigger. So here we are, 12 fermion, 6 quarks, 6 leptons, each a distinct note in the melody of matter. They're the clay from which the universe sculpts itself. But clay needs a potter. That's where the forces step in, shaping the chaos into order. If matter fields are the clay, force fields are the hands that mold it, the invisible threads that stitch the universe together. In the Standard Model, forces aren't vague notions of push or pull. They're dynamic exchanges, a flurry of particles zipping between fermions, like letters in a cosmic post office. These messengers are the bosons, and they carry the four fundamental forces that govern every interaction, from the spark of a neuron to the blaze of a supernova. First up is the electromagnetic force, the maestro of the everyday world. Its boson is the photon, a massless marvel born from the dance of electric and magnetic fields. James Clerk Maxwell first saw its glow in the 1860s, uniting electricity and magnetism into a single shimmering force. Photons are the light you see, the radio waves you hear, the X-rays that peer through flesh. But they're also the diplomats of charge. When an electron shoves another away, they don't collide. They trade photons, a rapid-fire volley that creates repulsion. It's the same trick that binds electrons to nuclei, forging atoms into the building blocks of life. Next comes the strong nuclear force, the brute of the bunch. Its boson, the gluon, is the toughest glue in nature, welding quarks into protons and neutrons with a grip that defies imagination. Discovered in the 1970s, through the haze of particle collisions, gluons don't mess around. They carry a property called color charge, not color you can see, but a quantum label with 3 shades: red, green, blue. Quarks swap gluons like kids trading crayons, ensuring their colors balance out in a neutral white inside protons and neutrons. This force is so potent, it leaks beyond quarks, binding nuclei together against the electromagnetic push of proton. Without it, atoms would unravel, and the universe would be a soup of lonely particles. Then there's the weak nuclear force, the subtle transformer. Its bosons, the W and Z, are lumbering giants, 80 and 91 times the proton's mass, born in the 1980s at CERN's particle accelerators. The weak force doesn't bind, it changes. It's the wizard behind beta decay, where a neutron spits out an electron and morphs into a proton, releasing a neutrino in the process. This alchemy powers the sun, turning hydrogen into helium, and drives the radioactive ticks of a Geiger counter. The W boson, with its +1 or -1 charge, flips quark flavors, down to up, strange to charm, while the neutral Z boson plays referee, mediating quieter exchanges. It's a force of metamorphosis, rewriting the script of matter one particle at a time. And what of gravity? The force that sculpted the cosmos, curving space-time around stars and planets, seems like it should join the party. Einstein's general relativity describes it beautifully, but in the quantum realm, it's a misfit. The Standard Model has no boson for gravity, no graviton to carry its whisper. Theorists dream of one, a massless particle rippling through space-time, but it eludes us, a shadow at the edge of our map. For now, the Standard Model shrugs and moves on, content with its trio of forces. These forces aren't just mechanics, they're history. In the 19th century, Maxwell wove electricity and magnetism into one. In the 1960s, Glashow, Salam and Weinberg braided the electromagnetic and weak forces into the electro-weak force, a unification confirmed by the W and Z's discovery. The strong force found its place with quantum chromodynamics, gluons painting the picture. Each step was a leap towards simplicity, a hint that all forces might once have sung in unison, back when the universe was a searing speck. But there's one more player in this orchestra, a field that doesn't carry a force, but shapes the music itself. To meet it, we'll need to chase the most elusive boson of all. Close your eyes and imagine a universe without weight. A frantic blur where every particle races at light speed and untethered, unbound. No atoms, no solids, no you. That's the cosmos without the Higgs field. A silent presence that slows the rush, giving substance to the ethereal. It's the final act of the Standard Model, a twist so profound, it took half a century to prove. The story begins in the early 1960s, when physicists hit a wall. The electroweak theory demanded massless W and Z bosons, but experiments showed they were anything but. Photons flew free, electrons dawdled. Why the difference? In 1964, a quiet Scotsman named Peter Higgs, alongside Robert Brute, Francois Englert and others, offered an answer. Space isn't empty, it's soaked in a field, a sticky web that clings to particles, dragging them down. The more they wrestle with this field, the more mass they gain. Photons glide through untouched, massless as ever. Quarks and leptons snag a little. W and Z bosons a lot. It was a bold guess, elegant in its simplicity. But a field isn't enough. You need proof it's real. Every field has its particle, a ripple you can pluck from the fabric. For the electromagnetic field, it's the photon. For the strong force, the gluon. For this new field, it's the Higgs boson, a heavyweight ghost that demanded a new kind of hunt. It's not stable. It decays in a trillionth of a second, so you can't catch it sitting still. You have to make it, smashing particles with such ferocity that the Higgs field quivers and spits out its boson. Enter the Large Hadron Collider, a marvel of engineering beneath the Alps. Picture it, a 17-mile loop of steel and magnets, chilled to minus 271 degrees Celsius, colder than the void between stars. Protons whip around it at 99.9999991% the speed of light, crashing in explosions that mimic the Big Bang's fury. Built by a global army of scientists, the LHC was a bet on the Higgs, a $10 billion wager. That nature's deepest secret could be teased out of the debris. The hunt spanned decades. Early accelerators hinted at the Higgs, but they lacked the punch. By 2008, the LHC roared to life, and two colossal detectors, Atlas and CMS, stood ready, each a labyrinth of silicon and steel, sifting through 1 billion collisions a second. Physicists pored over the data, tracing ghostly trails of energy, hunting for a blip at 125 GeV, a Higgs boson's calling card. On July 4th, 2012, the wait ended. In a hushed auditorium at CERN, spokespeople unveiled the evidence. A peak in the noise. A new particle. The Higgs. Cheers echoed worldwide. Higgs, now an old man, smiled through tears. It was the climax of a 48-year quest. What does the Higgs do? It's the spark that ignites mass. When the universe was born, a hot soup of massless particles churned in chaos. As it cooled, the Higgs field switched on, like frost settling on a window, and particles took on weight. Without it, quarks wouldn't clump into protons, electrons wouldn't orbit nuclei, and matter as we know it wouldn't exist. It's the breath that turned a formless void into a structured cosmos. Yet the Higgs is more than a finale. It's a question mark. Why is its mass 125 GeV? Not more, not less. A tweak either way, and the universe could unravel or collapse. It's a cosmic tightrope, and we don't know who's balancing it. Some whisper of extra Higgs bosons, others of links to dark matter, the unseen 27% of the cosmos. The LHC keeps probing them, but the Higgs holds its tongue, a sentinel of the known and the unknown. The Standard Model stands complete, a tapestry of fields, quarks, leptons, bosons, Higgs, woven with breathtaking precision. It predicts particle decays to a dozen decimal places, a feat unmatched in science. But it's not perfect. Gravity slips through its fingers. Dark energy looms unexplained, and the antimatter that should mirror our matter is missing. It's a triumph with a shadow, a peak with a cliff beyond. This is the tale of Chapter 3, a journey from the atom's heart to the edge of comprehension, driven by dreamers who dared to ask what we're made of. The Standard Model is their legacy, a symphony of fields that hums through every speck of existence. But the music isn't finished. New notes are waiting, and the next chapter beckons. Picture yourself standing beneath a night sky, so vast it swallows your sense of scale, a canvas of stars stretching into infinity. Now imagine that everything you see, the twinkling lights, the swirling galaxies, the very ground beneath your feet, makes up just a sliver of what's out there. Welcome to the edge of modern physics, where the Standard Model, our best map of the subatomic world, runs out of ink. It's a map that explains the particles and forces we know, quarks, electrons, photons, but fades into shadow. When faced with the universe's greatest enigmas, dark energy, the matter-antimatter puzzle, and the ghostly neutrinos that whisper secrets beyond our grasp. These are the mysteries that pull us forward, daring us to explore what lies beyond. Let's start with dark matter, the invisible architect of the cosmos. Back in the 1930s, a Swiss astronomer named Fritz Zwicky peered through his telescope at the Coma Cluster, a bustling congregation of galaxies 320 million light-years away. He noticed something odd. The galaxies were zipping around far too fast, defying the gravitational pull of the visible matter. It was as if an unseen hand held them in a place. Zwicky dubbed this phantom presence dark matter, a name that stuck like a riddle unsolved. We can't see it, touch it, or catch it in a net. It doesn't emit or absorb light, but its gravitational fingerprints are everywhere. Take the spiral arms of galaxies. Stars at the edges orbit at speeds that should fling them into the void, yet they don't. Something massive, something hidden, keeps them tethered. How massive? Picture this. If you tallied up all the atoms in every star, planet, and gas cloud, you'd account for just 5% of the universe's mass energy. Dark matter, by contrast, weighs in at 27%, a silent giant shaping the cosmic landscape. One of its most dramatic reveals came in 2006, with the Bullet Cluster, where two galaxy clusters collided at breakneck speed. The visible matter, hot gas and stars, slammed into each other, slowing down, but the bulk of the mass, traced by gravitational lensing, sailed right through, untouched. That was dark matter, aloof and mysterious, passing like a ghost through the chaos. What could it be? Scientists have their suspects. There are weakly interacting massive particles, or WIMPs, lumbering giants that might bump into detectors, deep underground, where experiments like Xenon 1T in Italy wait in the dark for a telltale flicker. Then there are axions, feather-light particles born from theories, tying dark matter to other cosmic conundrums. Telescopes scour the skies for gamma rays, from dark matter annihilations, while labs listen for the faintest whispers of its presence. Yet after decades, it remains a shadow on the wall, real, undeniable, but just out of reach. Now shift your gaze to dark energy, the force rewriting the universe's destiny. In 1998, two teams of astronomers, chasing supernovae across the sky, stumbled onto a bombshell. The universe isn't just expanding, it's speeding up. Picture a balloon inflating faster with every breath, driven by an unseen pressure. This is dark energy, a cosmic enigma that fills 68% of the universe, dwarfing both ordinary matter and dark matter combined. Albert Einstein once toyed with a similar idea, a cosmological constant to keep the universe steady, only to discard it when expansion was confirmed. He called it his biggest blunder, but today, that constant might be dark energy's true face, a vacuum energy woven into space itself. What does it mean? If dark energy holds steady, the universe could stretch forever, stars winking out one by one, until nothing remains but a cold, dark expanse. Or it might grow stronger, tearing apart galaxies in a cataclysmic Big Rip. Astronomers are racing to crack its code, wielding tools like the Dark Energy Survey, which maps millions of galaxies, and the upcoming Euclid satellite, set to trace the universe's growth over 10 billion years. Each measurement is a clue, but the full story of dark energy stays tantalizingly out of sight. Then there's the question of why we exist at all. Rewind to the Big Bang, a furnace of creation where particles and their antimatter twins, mirror images doomed to destroy each other, burst into being. They should have cancelled out, leaving a universe of pure energy. Yet here we are, built from matter, this with antimatter a rare guest. For every billion particle-antiparticle pairs, one extra matter particle slipped through the annihilation, and a survivor that became us. What broke the symmetry? In 1967, Andrei Sakharov laid out the rules. New physics, beyond the standard model, must tilt the scales. Experiments hint at this tilt. Particles like kaons decay in ways that favor matter. But it's not enough. The answer lies in uncharted territory. And don't overlook neutrinos, the universe's shy travelers. Billions stream through you right now, born in the sun's core, or the Big Bang's echo, barely brushing the world as they pass. They're the second most abundant particles after photons, yet they defy the standard model by having mass, tiny but real, revealed through their ability to morph between flavors as they zip along. Could they be their own antiparticles, a quirk that might explain matter's victory? The hunt is on, from icebound detectors in Antarctica to labs probing their oscillations, each result a breadcrumb towards a bigger truth. These mysteries aren't loose ends. They're the threads of a tapestry we've only begun to weave. They challenge us, thrill us, and promise that the universe is far stranger and more wondrous than we ever imagined. So how do we chase these cosmic riddles? We build a machine to rival the stars. Beneath the rolling hills of Switzerland and France lies the Large Hadron Collider, a 27-kilometer ring of steel and science, pulsing with the energy of discovery. It's the world's mightiest particle accelerator, a cathedral of human ambition, where protons race at 99.9999991% the speed of light, slamming into each other with the force of creation itself. This is our window into the subatomic wilds, a tool to peel back the universe's skin and glimpse what lies beneath. The LHC's story begins with a dream, to recreate the Big Bang's first heartbeat. Picture two beams of protons, each a swarm of billions, hurtling in opposite directions through tunnels, chilled to minus 271 degrees Celsius, colder than deep space, guided by magnets stronger than any on Earth. At 4 points along the ring, they collide, unleashing energies unseen since the universe was a newborn. Detectors the size of buildings, Atlas, CMS, Alice and LHCb, stand watch, capturing the wreckage in a digital storm of data, petabytes pouring in every second. It's a symphony of chaos, conducted by over 10,000 scientists from 100 nations, united in a quest that knows no borders. The LHC struck gold in 2012, unearthing the Higgs boson, a particle whispered about since 1964, Peter Higgs and Francois Englert had predicted it, a key to why matter has mass, and the LHC delivered, smashing protons until the Higgs flickered into view, a triumph crowned with a Nobel Prize. But that was just the opening act. The standard model, now complete, still leaves those mysteries. Dark matter, dark energy, the rest, dangling like unanswered letters. So the LHC presses on, its beams sharper as its detectors keener, hunting for the next breakthrough. What might it find? Supersymmetry is one hoped, a theory where every particle has a shadowy twin, a super partner. These twins could be dark matter's missing pieces, heavy and elusive, waiting to be born in the LHC's fiery collisions. So far they've dodged us, but the search narrows with every run. Then there's the whisper of extra dimensions, realms beyond our familiar three of space and one of time, curled into loops so tiny we'd never notice, unless the LHC catches gravity leaking into them, a clue to why it's so weak compared to nature's other forces. And the Higgs itself? Scientists dissect its every decay, measuring angles and energies for the slightest hiccup that might signal new physics. Running this beast isn't simple. In 2021, the LHC roared back to life for its third act, upgraded with tighter beams and higher luminosity, more collisions per heartbeat, to coax out rare events. Imagine sifting through a sandstorm for a single gold grain. That's the challenge. The high luminosity LHC, slated for 2029, will crank the dial further, flooding detectors with 10 times the data. A deluge that could drown or deliver us. Every tweak, every terabyte, is a bet on the unknown. Meet Dr. Elena Rossi, one of the LHC's torchbearers. She spent 15 years chasing particles, her days a blur of coffee and code. As she pores over collision maps, "We're explorers," she says, "mapping a land no one's seen. Most days it's noise, but one day it'll be a signal that changes everything." Her story mirrors thousands. Engineers in Geneva, physicists in Mumbai, students in Tokyo, all part of this global dance where, as Fabiola Gianotti, CERN's leader, puts it, the LHC is humanity's bridge to the invisible. This machine isn't just metal and math. It's our boldest leap into the abyss, a wager that the universe will share its secrets, if we dare to ask. While the LHC hurls protons into the void, another breed of seeker probes the universe. With pen and mind, these are the theorists, architects of ideas, building castles of equations to house the mysteries machines alone can't touch. They don't smash particles, they shatter assumptions, asking, what if space isn't what we think? What if gravity's a trick? What if reality itself is a shadow of something deeper? Their work is a high-wire act of imagination, tethered by the unforgiving rope of mathematics. Take string theory, a vision so wild it rewrites the rules. Forget particles as dots. Picture them as infinitesimal strings, vibrating in a cosmic orchestra. Each note, each wiggle, becomes a quark, an electron, a photon. It's a radical tune, promising to marry quantum mechanics' jittery dance with general relativity's smooth sweep. Gravity, in this world, isn't a force but a melody played by strings, rippling through space-time. The catch? It demands extra dimensions, 10, maybe 11, folded into shapes smaller than an atom, invisible but essential. Edward Witten, a string theory titan, spun M-theory from this, suggesting our universe is a membrane, adrift in a higher dimensional sea and a brain among countless others. But strings sing a tricky song. They predict a landscape of possible universes, 10 to the 500, a number too vast to fathom, leaving us wondering, is ours special, or just one roll of infinite dice? Critics argue it's untestable, a beautiful dream without a wake-up call. Yet its defenders, like Brian Greene, see it as a glimpse of the cosmic score. String theory tries to weave the universe's threads into one cloth. Other minds chart different paths. Loop quantum gravity imagines space-time, not as a smooth sheet, but a web of tiny loops, each a quantum stitch. Zoom in far enough, and reality pixelates, a grainy fabric where gravity bends and snaps in discrete steps. It sidesteps extra dimensions, rooting itself in the four we know. But its math is a labyrinth, still untamed. Then there's Eric Verlinder's heresy, gravity as an illusion, emerging from the tangle of quantum information, like heat rising from a crowd. Space-time, he says, might be a hologram, sir, its rules written in a code. We're only beginning to read. These ideas stretch the brain. If strings need extra realms, where are they? If loops dice up space there, what's between? If gravity's a byproduct, what's the source? Quantum information theory adds fuel, hinting that entanglement, the spooky link between particles, might stitch space-time together. Black holes, those cosmic sinkholes, become labs for this thought. Their edges a battleground where physics duels itself. Theorists don't just ponder, they prophesy. Einstein scribbled relativity on paper. Years before, eclipses proved him right. Today's dreamers, wielding supercomputers and chalkboards, plant seeds for tomorrow's harvest. Supersymmetry. Once the LHC's darling lingers in their equations, its superpartners still possible. Despite the silence, extra dimensions tease at gravity's weakness, a puzzle the standard model shrugs off. And quantum gravity, the holy grail, glimmers just beyond reach, a theory to bind all others. Their tools, mathematics, the universe's mother tongue, from Newton's fluxions to Dirac's deltas, it's the lens that reveals truth. Today, it's tensor fields and topology, a language so precise, it predicts worlds we can't yet see. This isn't idle musing, or it's a lifeline to the next frontier, where the LHC's sparks might one day meet the theorist's flame. We stand at a crossroad, peering into a universe that whispers its secrets in riddles. The standard model lit our way, but its glow fades against the vast unknown. Dark matter looms, dark energy surges, and the rules we cling to bend under scrutiny. The LHC roars with humanity's defiance, while theorists sketch maps to lands uncharted. Together, they weave a tale of wonder and grit, a quest not for endings but for beginnings. The universe doesn't yield easily, but that's the thrill. Each mystery a challenge, each answer a door to more. So we march on, eyes wide, hearts ablaze, chasing the question that echoes through time. What are we made of? From the earliest days of human curiosity, we've sought to unravel the fundamental building blocks of nature. This documentary has taken us on a remarkable journey, from the periodic table's elegant organization of elements to the chaotic subatomic world of the particle zoo, which gave rise to the Standard Model. We've explored the quantum realm, where fields form the true fabric of reality, and ventured beyond into the enigmatic territories of dark matter and unknown forces that shape our cosmos. Yet our understanding is far from complete. Dark matter and dark energy, the elusive nature of gravity, and the pursuit of a unified theory remain as frontiers yet to be conquered. Science, as we've seen, is not a finished story but an ongoing adventure, one fueled by questions as much as answers. As we look to the future, we stand on the threshold of new revelations, driven by the same inquisitive spirit that has always propelled us forward. In the words of Carl Sagan, somewhere something incredible is waiting to be known. With that promise, our quest continues, to peel back the layers of reality and discover what we are truly made of.